Okay guys, in this video we are going to be writing out electronic configurations, and we are going to be using something called the Aufbau Principle, which we're going to use to help us generate the ground state electronic configurations for many of the atoms within the periodic table. The word Aufbau, I believe, is a German word that roughly means building up. So this is the building up principle for electronic configurations. The diagram on the left is often used to show what orbitals you should fill first when trying to generate a ground state electronic configuration. It's a little complicated. I, for one, really can't memorize this diagram, so I have a hard time with it. I prefer to use simply the block structure of the periodic table, and I think that's what most people use. The periodic table has what we call a block structure in the sense that certain groups correspond to certain atomic orbitals. For example, groups 1 and 2 plus helium are called the s block of the periodic table. And so atoms within this position, atoms within a given position in the s block, correspond to putting an electron into an s orbital. So for example, when you put one electron into an atom, it starts by going into the 1s orbital. If you're at the lithium position, an electron, so for example the third electron into an atom, that third electron goes into the 2s orbital. Note that the period number on the periodic table corresponds to the principal quantum number in this sense. The block over here corresponds to the p atomic orbitals. So after you've put in 1, 2, 3, 4 electrons, so you've filled the 1s orbital, and then you've filled the 2s orbital, then you start filling up the 2p orbitals. So boron corresponds to 1 electron in a 2p orbital, carbon, 2 electrons in the 2p orbitals, nitrogen would be 3 electrons, and then the 2p orbitals themselves, all 3 of them, can hold a maximum of 6 electrons. Okay, so this row of atoms, when you're filling in electrons in an atom, they correspond to putting electrons into a set of 2p atomic orbitals. Once you've filled those up, then you start filling electrons in the 3s orbitals. Once that's filled, then you start filling up the 3p atomic orbitals, then the 4s, and then notice what happens here. After you've filled up the 4s, you start filling in the 3d atomic orbitals. And here what I want to point out is that the principal quantum number that you use for the d block is actually 1 minus the period number, right? So here for the 4s, or for the s block, the period number is the principal quantum number that you use. But when you're filling in d electrons, it's the period number minus 1. Okay, so after the 4s, then you start the 3d, then you go back to the principal quantum number of 4 and start filling up the 4p. After that, it's the 5s, and then notice here, you start filling in the 4d, then you go back to 5, the 5p then gets filled in, then the 6s. For period 6, then you jump down to the F block. The inner transition metals constitute the F block. So after 6s gets filled up, then you start filling in 4f. And notice it's the period minus 2. So the principal quantum number that you use for the F block is the period number minus 2, the 4f in this first case. Then you start filling in the 5d orbitals, then the 6p, now to the 7s, and then to the 5f, then the 6d, and so on. So this is the block structure of the periodic table. It's very handy for generating electronic configurations, ground state electronic configurations, and it's something that we want to learn. And so on the next example problem, we are going to be generating ground state electronic configurations for different atoms using the Aufbau principle. And so I'm going to pull up my periodic table, and we're just going to go through a bunch of examples. We won't do all 36 atoms that we're asked to do, but we'll do quite a few of them. So we're going to start with hydrogen. And what you want to do is to put in the first electron. Okay, and so this is the s block. The period number is 1, so that first electron goes into the 1s orbital, and there's one of them. For helium, okay, helium is still in the s block. We've put in a second electron. That electron is going to go into the s orbital, so it's 1s2. Now, after we've filled the 1s orbital, it's time to start putting electrons into the 2s orbital. So lithium is going to have the electronic configuration 1s2, 2s1. Beryllium, we're going to put in another electron, 1s2, 2s2. When we go to boron, we're going to jump across the periodic table into the p block. So the electronic configuration for the ground state of boron would be 1s2, 2s2. Now we start putting electrons into the p block. For carbon, there's 2 electrons in the p block, 1s2, 2s2, 2p2. Let's jump ahead to oxygen, 2p4. Notice this, so starting at boron, 1, 2, 3, the 4th p electron. Okay, so that's why it's 2p4. For fluorine, it's going to be 2p5. And then for neon, it's going to be 2p6, a completely filled n equals 2 shell. In fact, all of the noble gases have a completely filled p subshell. All of the group 2 atoms have a completely filled s subshell. Let's go ahead and do sodium, and what I want to do is illustrate the core notation. So starting with sodium, let's go ahead and do the full electronic configuration for sodium. So it's going to be 1s2, 2s2, 2p6, right? That takes us over to neon, and then to sodium, 3s1, right? The period is 3. This is the s block, so it's s1. That's the full notation. Very commonly, though, we use a core notation, a noble gas core. Notice that this portion of the electronic configuration is identical to neon. And so we will use this in brackets neon to denote the core electrons of the sodium atom. And we'll include only explicitly will only include the valence electrons, so the 3s1. For magnesium, it would be neon core 3s2. Let's jump across the periodic table and do phosphorus. So phosphorus, I'm going to say, has a neon core. The 3s2 is filled, and then we have 1, 2, 3 p electrons, so this would be 3p3. Let's go ahead and do some D block atoms. So let's try scandium here. So scandium is going to have an argon core, right? Argon, then to the next row. These are going to be the valence electrons for scandium. Okay, so it's going to be 4s2 and then 3d1. I think commonly, even though this is the order in which you fill them, it's very common to see people put the 3d1 before the 4s2. Okay, that's not I think this is actually the more conventional format. So you fill them out using this block structure, and then it's very common to then reorganize the electronic configuration such that the principal quantum numbers of the lowest value are first, followed by the higher ones. And there's actually a reason to do that we'll talk about at the end of this video. Let's do vanadium. Argon core, 4s2, and then we have 1, 2, 3 d electrons. So 3d3, and to be conventional, we will put the 3 d's first, followed by the 4s electrons. So this is the proper format for it. There are exceptions to the Aufbau principle. Let's show you one of those, or a couple of those actually. Let's do chromium. Okay. So first, what I'm going to do is show you the chromium, the Aufbau principle for chromium. So argon core, then it's 4s2, and how many d electrons do we have? 1, 2, 3, 4. So this is what the Aufbau principle would predict, and we would probably write it like this. Let's go back a couple of slides and look at what the experimental ground state electronic configuration is for chromium. We're going to find it's not the same. So here we have chromium. We see that it's 4s1, 3d5. Okay. Note, so this is what the experiment predicts. Argon 4s1, 3d5, and then if you sorted them, you would have argon 3d5, 4s1. So notice how they're different. The Aufbau principle tells you to fill the 4s, then start filling in the 3d. But experimentally, that's not what has happened. Really, we have a half-filled d subshell and a half-filled s subshell. And it just turns out experimentally that this is the more stable electronic configuration than this one. This would be an excited state electronic configuration. And there's no way for you to predict that. Okay, so there's nothing that I can tell you that would lead you to expect that result, other than just to point out that it's an exception to the Aufbau principle. The Aufbau principle is really a rule. It's not a law by any means. Another exception, I believe, would be copper. So copper would have an argon core, according to the Aufbau principle, and then it would have a filled 4s2, and then you would have 3d9, 9 electrons in the d block. But if you look at the experimental, it's argon core, 4s1, 3d10. A completely filled d subshell seems to be preferable to a completely filled 4s subshell. Okay? And that's just the way it is. Sometimes these are called the rule for the half-filled subshells. Half-filled subshells seem to be more stable than partially filled subshells. And then full subshells tend to be more stable than partially filled subshells. Again, there's no way to predict that just by looking at the periodic table. You just need to be aware that there are exceptions to the Aufbau principle. And you can find them scattered throughout the this diagram here. Let's see, I'm going to go ahead and stop with this exercise, and I'll leave others for you for practice on your own. And we're going to talk next about what is called Hund's rules, which are used to determine how to fill up a partially filled subshell. So Hund's rules come into play when you have a partially filled subshell. For example, carbon. There are only 2 electrons in the 2p subshell. How should you fill these in? Let me illustrate that there are different possibilities. So, for example, in this example, for carbon, 1s, 2s, and then we've got the 3 2p's. The diagram that's shown, we fill up the 1s and the 2s, and then we have this configuration. Well, what about another possibility? For example, where you have this, these 2 are filled, and then why not put them both like that? Or put one like this and one like that. These are all different, these all correspond to different electronic states. Okay? And they are viable electronic states. The question is what would be the lowest energy among these different choices? Hund's rules tell us what those are. So Hund's rules are basically an analysis of the different experimentally known electronic configurations, boiled down to which states are most stable. And the rule is that the lowest energy arrangement of electrons within a subshell has a maximum number of unpaired electrons. So in these three states that I've shown you, and they are only a couple of the possibilities, the one that has the lowest energy is the one where you have the maximum number of unpaired electrons. So these two electrons are said to be unpaired. These electrons would be paired, and these are paired as well. One is up and one is down. Maximum number of unpaired electrons. The term paramagnetic refers to atoms that have unpaired electrons. So in this example that we have here for carbon, we would say that carbon is a paramagnetic atom. And because the electron spin acts like a little bar magnet, unpaired electrons are attracted by a magnetic field. So there's a magnetic interaction between a paramagnetic atom and a magnetic field. However, when all of the electrons are paired, the little bar magnets on the electrons, they cancel one another out. So a spin up electron cancels out the magnetic effect of a spin down electron, and vice versa. And so if all of the electrons in the atom are paired, there is no interaction with the magnetic field, or else it's very, very weak. This effect is important in bulk properties. For example, a regular magnet, one that you're familiar with, it's called a ferromagnetic material. In ferromagnets, the electron spins within the crystalline solid, they all align with one another. And so that's what gives rise to a macroscopic magnetic effect. So these electron spins, they're important. They have important ramifications for the properties of different materials. In any case, we need to be able to distinguish between paramagnetic atoms and diamagnetic atoms, and we use these orbital diagrams that show which electrons are in which orbital and what are their spin orientations. You need to be able to generate these types of diagrams, and you use Hund's rule that you need to keep the electrons unpaired in order to do that. And so in this next problem, we're simply supposed to write out the orbital diagrams for a bunch of atoms. And so let me try that. Here's my periodic table. And so let's go back to our list of atoms. So hydrogen's pretty easy. So here you have the 1s orbital. It has one electron in it. The spin is unpaired, and so we would say that hydrogen is paramagnetic. For helium, one electron is spin up, the other one is spin down. Helium is diamagnetic. Lithium, we've got the 1s orbital and the 2s orbital. Those are paired, but this electron is unpaired. So lithium is paramagnetic. Beryllium, 1s, 2s. The 2s would be filled. Beryllium would be diamagnetic. We've already done copper on the previous page. Let's do nitrogen to illustrate Hund's rules. So here, Hund's rules need to be utilized because we are going to have a partially filled subshell. Okay? So nitrogen has 7 electrons. Let's put them in the proper way according to Hund's rules. So 1, 2, 3, 4, 5, 6, 7. Notice how I kept the spins unpaired. That's what Hund's rule tells you to do. So you keep the spins maximally unpaired for as long as you can, and that's the proper way to fill in the ground state orbital diagram. So you have unpaired electrons here. So nitrogen is a paramagnetic species. Let's do oxygen. What happens when we make oxygen? So oxygen has an extra electron. We've got a total of 8 electrons. So here's how you fill them in. 1, 2, 3, 4, 5, 6, 7. Now the 8th electron, you have to put it down like that. Okay, so you start to pair them up. Oxygen still has unpaired electrons, so it is an example of a paramagnetic species. For neon, you've got a total of 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Completely filled, all electrons paired. Neon is a diamagnetic species. Let's do manganese. Manganese. So I'm going to use the, we're only going to focus on the valence electrons for manganese. And so there is a neon core, but we're only going to think about the 4s. And then there are 1, 2, 3, 4, 5 3d orbitals, okay? Corresponding to 1, 2, 3, 4, 5, 6, 7 electrons that need to go in here. 1, 2, 3, 4, 5, 6, 7. Notice how I left them all unpaired for as long as I can. That's Hund's rule. Okay, I will leave other examples, other atoms to you to work as exercises if you wish. And let's see, what do we have next? We have a discussion about ions. And so this is important as well. Filled shells and filled subshells seem to have additional stability. So for the main group ions, that is when you start removing valence electrons to form cations, or when you start adding electrons to form anions, the anion that forms tends to be isoelectronic with the nearest noble gas atom. Okay, let's see. The other rule for ions that you really need to know is that when transition metals lose ions, they typically lose their s electrons first. Okay, so even though you fill in the s electrons before you start filling in the d electrons, when you remove electrons to form cations, you remove the s electrons first. So let's look at some examples of that. Okay, so here we are being asked to generate the electron configurations for different ions. Let's make this a little smaller. There we go. So we'll start with sodium here. And I'm going to go ahead and put the ground state configuration for sodium. Sodium is going to have a neon core, and it's going to be a 3s1. Now, when sodium forms a cation, it loses that s electron. Sorry about that. There we go. It loses this s electron. So you wind up with just a neon core. So the sodium cation is isoelectronic with neon. It's probably best to write that as a helium core, 2s2, 2p6, like that. For the phosphide ion, let's do phosphorus again. So it was a neon core, 2s, this would be a 3s2, 3p3. Phosphide gains 3 electrons. That's going to completely fill the 3p subshell. So you're going to have a neon core, 3s2, 3p6, and this is isoelectronic with argon. Has the same electronic structure as argon. So there's something extra special about filled p shells, subshells. So a filled shell tends to be extra stable. Aluminum 2+, that's probably a typo. It should say the aluminum 3+ cation. Aluminum is a neon core, and then it's 3s2 and 3p1. Well, that would be the ground state of aluminum. And then when you go to form aluminum 3+, you're going to take away 3 electrons. It's going to lose all of its valence electrons, and it's going to have a neon core. And I won't bother to write that out, but just I wanted to point out that the cation that forms is isoelectronic with the noble gas. That noble gas completely filled p subshell is just extra stable. For parts D and E, again a typo, it should be, one should be iron 2+ and the other should be iron 3+. So we'll do iron 2+ first. So iron has a argon core, and then it's 4s2, and then we have 1, 2, 3, 4, 5, 6, 3d6. When you form iron 2+, it loses the s electrons first. So the transition metals typically lose their s electrons first. It's going to be a 3d6 configuration. For the iron 3+, it's going to be argon 3d5. So after you've removed the s electrons, let's say the atom has variable charge, the ion has variable charge like many of the transition ions do, then you start taking away the d electrons. Do I have more examples to try? No, I don't. So I'm going to go ahead and stop this video here, and we'll pick up with the periodic structure as it pertains to electronic configurations in the next video.